Alrighty, welcome back everyone. Um, created this little new presenter overlay thing. Well, I didn't create it. I just used like the Mac built-in stuff, and I'm really liking it. It looks way nicer than the previous little like box in the corner. But it's uh time to talk about Graham Schmidt orthonormalization. If you've been following along, you've seen like the behind the scenes video. Um, Quick thing, I think I'm gonna switch around a little bit how I'm gonna work on this. I'm gonna switch it more to that vlog style because I feel like the behind the scenes stuff was both more valuable for me, and I think actually is more valuable weirdly for you as well to be able to observe that thinking and, you know, understanding process. That is like the core of what I want to showcase with this channel, right? So I think I'm going to be doing more of those. I'm also going to do these crystallizing videos where I crystallize my thoughts into it. And I think I might still name this lesson 10 just because that was the thought process, but I might like figure out a new naming, or I might like stick with the lesson naming. But really, we're doing more of a vlog style, and it's very difficult to even say that this is a lesson or a tutorial because, like, sure, I have learned this stuff and I learned like, but in terms of what I actually showcase on this channel, I'm usually learning it a couple of days ahead of time. So I'm by no means expert enough to describe things in a way that connect with other things. And maybe someday I'll be there, but I'm not there right now. And I feel like it's a bit dishonest to say, like, come watch this and you're learning, right? It's not purely educational content in that way as much as it is. I wouldn't say it's entertainment either. It's more about like bringing you along on this journey of learning, right? So that's important for me personally. Um, so let's just get into it. I'm gonna start by talking about what what Gramscian orthonormalization is, um, and like more generically what orthonormalization is. We're gonna go through a few of the tabs that I've showcased in some of my previous videos and like describe and talk about it, and then we're gonna jump in the code, write it up, uh, do a quick test, and that'll be what this video is, right? So let's just get right into it. Right. So let's close that tab. You don't need to see that tab, or determining if my content is made for kids. I don't know what these YouTube tabs are. Oh, David Metzler. He was kind of a cool guy. Gonna close this. Okay. So we're just gonna essentially start from like because as you guys know, I've been using like ChatGPT a lot. You don't have to use it, but it's like a nice starting point to get you down into this rabbit hole of things, right? And it's a great starting point for like asking certain questions, but definitely don't rely on it. It does make mistakes, even like the really nice like reasoning engines and all that. They still make mistakes. And I've personally experienced that. So it's a great accelerator and a great enhancer, but be careful, and this is just something I've been using, like, because this like, kind of applies where you can kind of create coding exercises with this and kind of use that to develop this thing a little bit further, in terms of, creating a course for yourself and then following that along and using sources outside of ChatGPT to really learn it. I think that's really important. I'm just going to start off with this, and really what it is the process of taking a set of independent vectors, uh, doing a series of transformations and manipulations so that they're both orthogonal and unit length, right? So that's where the orthonormal thing is. Ortho is orthogonal. You have to get orthogonality, and you have to have them be normalized, aka make them unit length, right? Um, Maybe you've picked up on this already, but that also does involve our good old friend, the Euclidean norm, or, norming the vectors. That is a part of this process, and it's important. So trying to focus in on that is an essential aspect of this whole process. Um, Specifically here, there's going to be some time spent trying to understand this geometrically, because once you understand it geometrically, seeing the math kind of follows, right? Um, But as I've stated earlier on this channel, I think it actually behooves us to try and think about these things in the abstract. It really has a lot of value to think about this in abstract before going into the geometric representations, which help crystallize that abstract intuition, right? That's important. So, say you have a set of independent vectors in some vector space, right? Um, Also, a quick thing, orthogonal means perpendicular in 2 dimensions. It'll make like a right angle, but being perpendicular to each other is an important aspect, but that's a different story. Say you have a set of linearly independent vectors. Like, how do we do this? What is this Gram-Schmidt process for orthonormalization, right? So when you have this set of independent vectors, the first basis vector is very simple. It's just like literally whatever the first vector is and normalize it, aka divided by its magnitude, or if you want to, or the Euclidean norm or L2 norm as we have discussed earlier, right? Um, then you want to orthogonalize each subsequent vector. So how you do that is you make a projection of the vector onto the vector space of the previous basis vector. Now, what is a vector space in this sense? Like, so if I have a basis vector, like if I have a vector, right, in let's say 2 dimensions. In 2 dimensions, you have like a vector that goes like, I don't know, it has a magnitude of let's say 5 and it goes up to some point here. Some point, doesn't matter, right? The vector space for that vector is that entire line, right? So that full line that you create, that is what is constitutes the vector space. And we're really projecting onto that vector space the current vector, right? The mathematical or the algebraic representation of this is the taking the dot product of the previous um, of the basis vector with respect to the current vector and scaling that basis vector by the dot product, right? Mathematically, if you just try a few things, it works out. Also, I believe there is a I think there might be a geometric because dot products are represented algebraically, where it's like, A1, you have two vectors A and B, so it's A1, B1 plus A2, B2 plus. So that's the algebraic representation of a dot product. Similarly, there's a geometric representation of a dot product, which is like the magnitude of A times the magnitude of B, so the L2 norms, times cosine theta, basically, right? And the angle between those two vectors, right? So that's one another representation of it, and that it keeps getting more complicated. So let's not worry about that too much, right? So you project it onto that vector space, right? Then you take that vector and subtract it from that basis vector. And here you can see specifically the sum, right? And I have a couple of YouTube clips I pulled up by other people that I'm gonna play and show you. Like I'm gonna mute it. We don't need the audio of it, but just to geometrically showcase this later on, wherein essentially you want to take the sums of the projections for all of the previous basis vectors with respect to the current vector that is being orthogonalized and subtract it from that vector. And what that does is like first you have the projection vector. So you have to calculate that. So there's this vector here and this vector here. And this one has like this is the vector space, that full line as we discussed. And you drop a perpendicular onto it, onto this line, and that vector that gets created over there, that's the projection vector, right? When you subtract the current vectors, so that would be this vector, that second vector that's going on this way. And I'm speaking very abstractly, and I'll show you some visualizations that'll help crystallize this. When you have this vector, because I think it's very good to practice thinking abstractly, that perpendicular vector actually, to actually get the specific representation of that vector is what we're doing here, where we take the vector and subtract that by the sum of all the vector projections of that vector onto all the previous basis vectors, right? To get that orthogonal, like that perpendicular, that orthogonal vector, right? That's where the orthogonalization happens. And then you just divide that new vector by its own magnitude to get the orthonormalized vector. And that's basically all this is, right? There was also a point here about, let me just showcase this to you geometrically first before I get into checking the orthonormality via the dot products. That involves something called a gram matrix, and it's okay. We'll get to that. So let's look at this. So this is a video in 2 dimensions.
Full plane
Oh, I'm
unit.
just gonna
That's a
mute this
subspace
guy.
of
Gonna move
R3.
myself first.
And it
Right. So I'm just gonna move forward. It's a decent video to help me like get it, you know. I was also looking up images and stuff, but this is like a good two-dimensional example. So you have these two vectors, v1, v2, right? And then essentially at a certain point, so this v1 u1, this is the normalization of v1 to the basis vector u1, right? Then you want to project v2 onto the vector space of u1. So as you can see, there's this vector space of u1, right? And that's what a basis vector is, by the way. A basis vector is a vector that given a set of basis vectors, you can explore an entire vector space. So if you have, for example, in 2 dimensions or in Cartesian vector space, right? If you have two vectors that have at least some x component and some y component, they are considered and they're not parallel to each other, because that's important. As long as they're not completely parallel to each other, you can use those two vectors to explore all of Cartesian space in its infinity, literally all of them, right? And that's what a vector space is. That's what a basis vectors are, or vectors that you can utilize to explore a vector space, right? So all of Cartesian space or all of three-dimensional space, or in higher dimensions, uh, all of the n-dimensional space, right? And now, to be specific, I believe basis vectors really are about exploring the vector space. So you could have basis vectors that don't explore the entirety of the dimensional space, but that's a different story. I don't want to get gets more complicated. And orthonormal basis vectors, that's what we're really trying to get out of this, is get the orthonormalized basis vectors, because it simplifies calculations and there's a lot of other things, right? And also, this was a realization I had in a previous video where when you have it seems like a trivial example because you're essentially creating a new set of axes when you create an orthonormalized basis vectors from a set of linearly independent vectors. Like once this process is done, you'll see u1 and u2 are orthogonal to each other, and you could actually create an entire new graphing system that just relates to u1 and u2 that you'll see at the end of this video, versus something like um I'm gonna move this thing here so I can like look at it as I'm talking. The orthonormal um the two vectors, since they're orthogonal and they're unit length, so you can like half them or you can increase them, they could become like a new axis almost, right, in two-dimensional space. And I think why I hypothesize in n-dimensional space, that becomes really relevant because the concepts of having Cartesian space with x and y, or three-dimensional space with x, y, and z just doesn't, like, how do you do that in more than 3 dimensions or 4 dimensions? But the math works out, right? So I think creating almost that coordinate system, but instead of having an absolute system of here's x, here's y, here's the origin, blah blah blah, we create a coordinate system that's what's the word I'm looking for? That's relative to the vectors you actually have on hand, that can explore as much of that n-dimensional space, right? So that's my understanding. Once again, I could be wrong, and maybe as I'm moving forward in this journey, I'll crystallize it in a different way and understand it in a different way. And so maybe I'll be wrong. So yeah, I'm just gonna get to playing this video again. So as you can see, so the first one is like the projection. So this over here is the project. I'm gonna move my thing back over here. This over here is the projection, right? Projection vector. And when you subtract from V2 this projection vector, you get this perpendicular vector, right? This V, like, I actually don't know what that upside down T symbol is too. That is actually the vector we're looking for. We have already orthogonalized it. After we take the projection and we subtract V2, we get this. So this is the orthogonalization process, right? And then you move that over here. That's just for better representation that they're all orthogonal. And now he scales it. I'll show that, and boom, orthonormalized. So there's actually, even if you go to the Wikipedia page, There's Gram-Schmidt orthonormalization, orthogonalization, and orthonormalization. They're actually two separate processes that are combined into one process in the ChatGPT thing, right? And in fact, it took me a while to understand this because um, the actual what's the word I'm looking for? Equation for a projection is the dot product of v and u. That's what these angle brackets with the comma means, is a dot product, right? So v dot u over u dot u, so the dot product with itself, and then scaling the basis vector based on that. And that was confusing. I'm like, okay, why didn't ChatGPT tell me that, right? And that took me a while to figure out, but that's basically here because here they keep it separate from the normalization process. Whereas here in sorry, I'm just gonna pause this really quickly. I will show that video to you in a moment. Here we each basis vector is already normalized. So if you divide here in the projection by the basis vector itself, or the basis vector's dot product with itself, it doesn't make sense because the dot product with itself will just be one. So you don't really change much, right? Um, so this is another visualization in 3 dimensions, and this one is really nice because it kind of showcases the need for why we subtract the vector from the sum of all previous from the sum of the projections of this vector onto all previous basis vectors, right? So here in this first step, like you get these components of the projection onto the existing basis vectors u prime and v prime as shown here, and then you see this other vector, right? This is like the sum of these, and you sub take away w vector minus this whole thing gives you the orthogonal vector. That's the actual orthogonal vector, and then you take this vector and divide it by its own magnitude to get the orthonormalized vector, right? So I think that captures everything that is needed here. um I will talk just one other thing that I think is an important concept in terms of how do you verify orthonormality is checking on the diagonal or off diagonal, which was like, wait, what did that mean? And it really is about creating this thing called a gram matrix right here, right? So basically, the gram matrix is you take the pairwise dot products of all of your basis vectors in every combination, right? So here it's showing you UI, UJ. Oh, my laptop's charges. Anyways, never mind. UI, UJ, and that's I from 0 through n, or 1 through n minus 1, whatever. Like, and same thing with J, 0 through 1. So all of the combos humanly possible, right? And where I equals J, right, when essentially it's the vector's dot product with itself, it's 1. And then on the off diagonal entries, meaning a dot product with any other a dot product between a basis vector and any other basis vector other than itself, it's going to be 0. Why? Because the vector's dot product with an orthogonal vector will be 0, right? And that kind of follows from the geometric representation. Remember how I mentioned that a the magnitude of A times the magnitude of B times cosine theta is actually the geometric representation of the dot product, and the cosine of 90 degrees is 0. So if it's perpendicular, it's orthogonal, that whole thing comes to 0, right? And I believe there's a proof from the algebraic representation to the um from the algebraic representation to the geometric representation, but I didn't quite understand it fully, so I'm not gonna talk about that too much. But it exists, so that's like a real thing, right? So I think that's everything. Let's just look at the actual algorithm or the math or whatever. I was prompting back and forth, asking small weird questions, asking it for more examples and things. Also, all the way in between while googling other things. So as you can see, there's like a lot of tabs here. I'm not gonna go through all of them because I feel like I was doing that earlier and it's just not useful. I think having that vlog style where I'm just talking and thinking and Googling things and all that, and having this one more crystallized video is more useful on both ends because this can actually be used as a learning tool, as well as those other videos can be more in terms of like following along in the process kind of video, right? And it could also be an inspiration, one of those videos. Like if you see one of those videos, like you start thinking about yourself and you're like, I don't finish up in those videos because I'm also still learning and thinking. And you'll be like, before I come to my next video, you might get inspired and start thinking about it yourself and exploring it yourself. And it's fun. It's fun. I think that's fun. At least that's really what I'm hoping and planning to do here is just spark that curiosity. That would be awesome. That's like the biggest thing. Anyways, so I'm not going to go into the numerical illustration. So as I said, the first basis vector is just the first vector normalized. That's it. It's very simple. The second vector onwards, you take the projection of that vector with respect to all previous basis vectors calculated so far, right? You subtract the sum of all of those projections from the vector of concern, and then you normalize that new vector, and that's how you get it's actually fairly straightforward once you get all the other moving pieces. Like initially when I saw this, it took me like I could read it and understand it, but I'm like, why are we doing this and da da da. But now you have all the moving pieces, all the context, it makes a lot more sense, right? and and boom, and things actually, like I didn't struggle with this nearly as much as like with actually doing the algorithm for something like Gaussian elimination, but I spent a lot more time just understanding and thinking about this, because I think up till Gaussian elimination I had an intuitive sense of things, and this one I'm like, I didn't have that feeling or intuition as much. So I spent a lot more time just making sure I understood why. That's always another thing when it comes to learning. Don't take anything for granted. Ask everything like why. Why are we doing this? Why are we doing this like this? What is the usefulness? And sometimes there's almost always going to be answers. Sometimes you're not going to understand those answers, but that's okay. We've talked about this concept before of the rabbit hole bedrock or the intellectual bedrock. You'll hit that point where you're like, okay, I'm starting to not understand this. Well, the thing is, like, as you continue on a journey, and as long as and if you continue on in one field of studies, eventually you start chipping away at that bedrock. I've had those moments many times in the past where something feels like this is impenetrable, and then just through repetition and coming back to it again and again from different angles, because I'm like, okay, I don't understand this. I'm going to go back and I'm going to do other thing. I'm just going to move on to the next thing. And then next thing also is usually because it's some line of study or thing I'm trying to learn. It kind of brings me back to that similar context and maybe a different point of view. And eventually that bedrock just gives way and it's like, oh, okay. Anyways, so this is fairly straightforward. We're just gonna go straight into the code now. The code is, the way I did it, and I'll give you a sneak peek, but I'm gonna try and do things from my head, is a lot of things that are small pieces that we've actually already done before. So like doing the dot prod is going to be a thing here. So dot prod a comma b equals, and I've come a long way from doing the typing hints and all that. That was like fun for the dot product thing, because I want to turn that into more of a challenge. But after that, I'm like, this is getting irritating, and it's not really the key to what I'm learning. But like, always feel free to challenge yourself. If you find even this stuff is like not challenging and you're trying to refresh this for yourself, make that challenge. Why not? Like, make it like part of the reason why I'm doing this is both to learn and understand the math, but also to improve on the engineering skills and algorithmic thinking and all of that, because that's also important, right? Like Gaussian elimination was a great example of this. Is when I was doing that, intuitively I knew how to do Gaussian elimination. It's actually a very simple and straightforward process, and why you're doing all of that. But like writing the algorithm for it, I was like, oh my god, I'm gonna kill myself. Like, how does this? I'm not literally gonna kill myself. That's not a nice thing to say, and please seek help if you're having problems. But I was like, oh my god, this is horrible. um Anyways, so we the dot product is the sum of all the pairwise elements multiplied together, so it's a times b idx, I think a underscore n, let's say that, for a underscore n in, oops, in enumerate a, let's say let's put idx here. Boom, that's our dot product. I'm not even gonna bother. I'm gonna do a lot of the code just like bam bam bam. I'm not gonna test. And honestly, gotten to a point where I'm confident enough to be able to do that. Even when I'm learning for myself, I'm like, okay, I'm just gonna think and just write, and it'll be fine. But I definitely, if you are at home, if you're more newer on the coding side of things, please be testing things as you go along, right? Um, and doing it in Jupyter Notebooks is, and Python is a great language for picking up, and Jupyter Notebooks is great because it's very easy to view output very quickly. Um, and they have tons of resources in terms of support and learning and all that jazz. So okay, dot product is here. Okay. What's another common operation is okay, so we're going to take the dot product and we're going to multiply it by this other vector. So scaling a vector is important. So scale um m comma a, let's go with that. And that's just return, because I'm not using NumPy arrays. I just wanted to do everything from scratch, even though like the task itself was to do this in NumPy arrays. But I'm like, nah, I'm gonna do this by hand because I'm a badass. So this is just gonna be return m times n for n in a, and that's about it. For scaling, right? I think there's a couple other things. Let me just take a quick sneak peek. Yeah, the norm, of course, we need the norm, L2 norm. Um, Norm is just gets a vector, let's call it A. And L2 norm is the sum of, I'm just going to do the square root part earlier because it's the sum of the squares, uh, the root of the sum of the squares, right? The square root of the sum of the squares. So the squares are n 2 raised to 2 squared for n in A. I think that's, yep, that's the L2 norm. That's easy. So vector subtractions and additions, that's like pairwise subtractions and additions. Vec sub, we can go A and B. Return n minus b idx for n in A. Let's go enumerate idx. I'm just like a fan of doing all this in one line. And we'll do the same thing for vec sum, because we're going to have to add vectors together as well, because remember we have to do the sum of all the projection vectors, right? My neck is killing me. Vec sum is also similarly, I'm just going to actually copy this and replace this minus with a plus. We're gonna do a quick function for projections as well. They're pretty straightforward. So I'm just gonna do this with u comma v just to make sure it's right in my head. And it's like literally just the scale of the dot prod, right, of u and v, and you scale u by it, right? The basis vector. This one I'm just going to double check really quickly. Yeah, so the projection is dot product view to u and v uh, up to and you scale the basis vector u by this dot product, right? So that's what a projection is. It's just like literally scale dot product. That's pretty straightforward. I'm going to do one final helper function, which is sum all vex, right? Because I have a sum function for summing the vector function, but when you're summing all the projections, you have to sum all of them. So I'd rather just have one function rather than write a separate loop for that. So that's going to be some set of, I'm just going to call them p underscore v, all the vector projections, right? That's what I'm going to call it. Sum vex equals p underscore v0. Wait, this does not need to be a list. And then for v and p underscore v colon sum underscore vex equals vec sum uh sum facts. So confusing. V, right? That's really all it is. And then we return some x. Oh, okay. I think that's all our helper functions in place. I'm just gonna go straight into the ortho norm now. GS ortho norm. I think that's fine. This takes a set of linearly independent vectors. How do we do this? So I'm gonna create linearly independent vectors. So it's just gonna be a list of lists. That's how I'm framing it in my head. Because this one was a little weird because there's kind of different ways to do it in my guess in terms of how I would like, for example, I could do star args and then just have each vector be passed as a separate argument that is turned into a tuple by the star args. If you don't know what star args or star quarks are, that's star args and star like the asterisks. I mean, when I say star, kwargs. If you're following along or looking at this stuff, like please Google it. It's very helpful concept in Python in terms of functions and the arguments for functions. Really important stuff. Like definitely look it up. It's really important. So let's just create and pre-allocate the spaces for a vector u equals none for underscore in li underscore v. So we just have an empty list of nuns, and each nun will be replaced by the basis vector, and that's we're just going to return this list of lists or list of basis vectors as the output, right? Okay. You will just go ahead and set up the first basis vector. I actually, when I did this myself, I did the first two basis vectors by myself and then jumped into the loop because I had made a mistake where in this step over here, where it's like doing the sum of the projections, I thought it was the sum of all previous projections, but it's actually the sum of all projections of the current vector onto all previous basis vectors, not just all previously calculated projections. That was dumb of me, right? So I was keeping a separate projections vector and I thought I had to do two. I was making it unnecessarily complicated. When I realized my mistake, I'm like, oh wait, I don't need to do actually both the first and the second basis vector before entering into the loop. But I'd already done it that way, so I just like kept going. So I'm going to do a little bit differently and just do the first one locally before entering into the loop, because the first one is a special case where it's literally just the first vector Euclidean norm. That's it, right? So that is scale 1 over L2 norm of Li underscore V 0, the first vector. We scale that, yeah, L2 norm, scale that by Li underscore V 0, right? Let's just confirm that really quickly by looking at the math. So like looking at math while developing these things is actually, I think, fine. It practices your ability to learn and understand math and then be like, okay, I'm doing this here. So like being able to translate between these two languages is kind of a nice and important skill. Even if you're going on the pure math side of things, there's so many simulations and things like that. That's like super helpful, I think. Right. I think that's fine. Even pseudocode is fine. I mean, like, do what you need to do to like get the thing done, right? Try to like do it from the raw source rather than the slightly computed source. Like if someone just gives you pseudocode, or the worst is like when you're just looking at the solved answer, the the lower down on that tree you go, like the closer to just being given the answer you are, the less attention you want to pay to it. I think you have to like mentally like willpower, like, okay, I'm really struggling. I do need to look, but I'm just going to take like a quick peek and like whatever my image snapshots, and then I'm just going to start thinking about that and go from there, right? You're going to want to do that, right? That's not the best way to get good at lead code, by the way. I think with lead code, just go ahead and do the answer and like really look at it, really spend time understanding it, and then doing it again from scratch, which is also viable. Uh, but mastering lead code isn't the same as mastering like data structures and like things like that, right? That's not the same, right? Because these kinds of things really work. This is why I think this is a huge problem with the education system. We don't actually educate people. We don't actually teach them things. We're actually teaching them how to pass an exam. That's essentially what we teach people. We don't really teach them stuff. We don't teach them math or English or this. We teach them how to pass or do well on math exams and English exams or whatever, pick a subject exam, right? And that comes to a real head like when you're in the super upper, like when you're on the PhD track and stuff like that, and you start like being like, it's not the same, right? Because there's loads of tips and tricks for like figuring out how to do really well in an exam. And there is a component of that that's really important to the thinking process and learning process, but it's not the same as like as deeply understanding it in the way to direct effective research, right? So this is just a me philosophically ranting. I'm just going to put this up again because I keep looking into the corner of the screen to look at myself to see if things are coming up. So yeah. Anyways, so this is what the projection is. That's exactly what we wrote here, right? So we're good. We're good. I think now it's time to get into the loop part of it. So for I in range len li underscore v, right? And we're gonna actually start from one because zero is already taken care of, like the first basis vector is already done. Len liv. Okay, I don't think we need to do anything there. For I in range one len liv. Okay, what do we do here? We need to get all the projection vectors, right? So let's create a list of all the projection vectors so far, right? Which is project, project what? Project u and v. So u, okay, let's just go u, and v is li underscore vi, right? That's the current iteration, whatever the current vector is, u. This is a list comprehension, as you guys can see already, or the starting of one. So for u in u, right? But we're not going through the entire u. We're going u through till the current element, right? So since this starts at 1, this will only iterate once on u0. And then once I is 2, it'll iterate 0 and 1. So like the previous two basis vectors, etc., etc. So you get all of the projections. Okay. And then we take the sum of those projections, right? I think we can skip a step here and do sum all vex right now and just do that, right? And get the p underscore sum. Actually, let's just call it p underscore sum because the big P in my head is like a matrix. That's why I labeled it like that. But since we skipped that part, I think when I did it myself, we'll look at that later. I'm just gonna put this here. Um, p sum, so that's the sum of all the projections, right? We have to do vex sub, and it is li underscore vi and e underscore sum, right? That's fairly straightforward. Oh my god, my neck is killing me. Oh, Jesus Christ. Sorry, guys. Um, and that we can just immediately put it into the next spot in u, and we're just going to do u I equals, and we're just going to norm this, which is, we're actually going to scale this by 1 over the L2 norm of UI, and we're going to scale that, right? UI, boom, done, right? And then we just return U. I'm not going to go through the process of explaining all of this, the orthonormal basis stuff, especially because this stuff gets a bit hairy. I got it generated, and so I also don't. I get the idea of what they're doing here. It's basically checking the diagonals, where it's like, remember how I told you the diagonals in the Gram matrix will be the dot products of the basis vector with itself, which will be 1. Otherwise, it'll be 0. So that's what these two lists, these three are doing. So it's just my test. I'm going to copy that. I'm gonna run this thing. I'm gonna pick that. I'm gonna copy paste this. I'm gonna do this. Oh, and there is an error. Where is the error? Of course, there's an error. Operand times for int and none type. Okay. For int and num type. Okay, we're known for doing these live debugging issues, so let's get to this one. So the problem is here. So it's either the problem with my scale function and the way I wrote it. 1 over L2 norm. What's wrong with the L2 norm function? Nothing. Okay, I don't understand what the problem is, actually. Okay. Let me just go ahead and print li underscore v0. Let's just do that. Let's see what the issue is if there's a print 110. Okay, so the vector is going in. Okay. Print 1 over L2 underscore norm of li underscore v0. Let's see if that is an issue. Oh, okay. Oh, because I'm not returning the L2 norm. I'm an idiot. Same thing with the dot product either. I just wrote those so fast I didn't bother to add the returns. That's a problem. Same thing with the project. I didn't put any returns. I'm so silly. Yeah, I think that should fix it. I'm just gonna comment out these print statements. I don't want to see like a bunch of prints of the asserts are passing. Nope, there's an issue. Vector 0 and 1 have dot product negative 0.5. Okay. Okay, for the interest of time, because it's like 2 a.m. and I haven't had dinner yet, I'm just gonna look at what I did here. Get some vec or some all vecs. Those are the same essentially, right? Okay, I'm very close. Let me double check I'm not crazy on this. Okay, so the asserts do pass in my previous code, so it's something I've done wrong. So the only thing I did differently was I didn't do the U1 separately and I jumped straight from U0. But the answer should be the same, I think, right? Okay, maybe I'm doing something wrong with the sum all facts. For U and U pull an I, no, and that part's fine. So what is the problem here? Having a dot product. Have I screwed up the dot product somehow? How do I do the dot product? No. Oh, it's about the same. Not about the same, it is the same. Scale, no, it's the same as well. L2 norm, sum n squared for n and v square rooted, yeah. Vex sub, yeah. Vex sum, yeah. Sum vex, yeah. Some sort of issue with numerical stability, perhaps, but I'm not sure. Hmm. Okay, I'm gonna do something I haven't done on these videos before because it is super duper late. And let's say we start by 2. Okay, no, the error still remains. Just weird. Victor 0 and 2 have. Oh lord. Okay, so I have screwed something up in this grand scheme of things. Oh my flippin' lord. None for underscore in. Wait, no, but then that shouldn't make a difference, should it? None for underscore in LIV. Would it? I think so, but I'll try. There's no way this is the problem. This is somehow the problem. That would be like crazy. No, that's definitely not the problem. That's what I thought. Okay. If I screwed up U0 somehow, 1 over L2 norm, scale this. 1 over L2 norm, scale this. Yeah, okay. M times N for N and A. Scale M times N for N and V. Whatever. I use V instead of A, but it's the same. So scaling is fine. L2 norm, let's look at that closely. Sum of N squared for N and A. Sum N squared for N and A square rooted. Sum N squared for N and V square rooted. Okay, so the L2 norm is fine. Vex sub return n minus b idx for idx comma n and enumerate a. Vex sub a comma minus n. Yeah, okay. Vex sub and sum don't seem likely to be a problem. Project scale dot prod uvu. Scale dot prod uvu. Okay, projection is correct. Project u. Project u for u in big U colon I. This is very frustrating. Okay. Wow. I'm gonna try something super weird. Just gonna overwrite that space. Okay, so the assertions, there is some pain here. Oh wait, this is the second one, not the first one. 2 colon LIV. This is making perfect sense. Only difference is here I split that apart and I do the sum ink in the next one instead of just putting it all here. Hmm. I literally can't tell a single line of difference. I've literally just like looked at my previous answer like completely. I don't understand what I did wrong. All right. Um, I'll have like an addendum video to try and figure this out and get back to you guys. I really need to call it. This is taking too long. But thank you all for being here on this journey, and I hope to see you guys again soon. Just remember to stay curious.